So, hello everyone. Uh, Happy Friday. So I recorded yesterday's lecture and I've put it up on YouTube. I need to give you all the link for the channel where I'll be keeping all the videos. But the idea is that I should be uploading all of these videos the day of, basically, so that if you can't watch one of the videos, you can go back and watch it on YouTube. Hopefully that's a good system. I haven't started taking pictures of my notes yet, but I'll try to do that today after class, and I'll post those on Sakai. So at some point this afternoon, you should have access to 2 videos on YouTube and 3 sets of lecture notes for the 3 days that we've been working. I also posted a new homework yesterday. I need to be more consistent about posting that immediately after class so that if people want to get started on work that afternoon, that's an option that's available to you. So I'll try to do better on that in the future. A lot going on in this class, but I'll make sure that new problems are available to you. So yeah, I now have a second homework posted. It'll be due on Tuesday after class, in keeping with the 3-day delay, basically, 3 class day delay. And then I'll give homework at the end of today that should be due Wednesday. Any questions thus far? No questions. Okay. So what I would like to do is I'd like to start off by finishing up my discussion yesterday, which was on the classification of differential equations. If you recall, we had kind of several steps in our classification. One step was, is it an ODE or a PDE? And this depended essentially on whether you've got partial derivatives floating around. To have partial derivatives, you've got to have functions which are functions of several variables. So as I said, we'll mostly be focusing on the ODE side of things. We also discussed systems of equations. Or systems of differential equations. Essentially, the nice way to think about this, remember this, is that there should be nice models to determine how populations of predators and prey are interacting with each other. And so you're going to have 2 functions that you're interested in: the population of the predator species and the population of the prey species, and those should be interacting. So the d over dt of p, if p is the predator, should depend on the number of predators and prey, and similarly, the way that the prey population is changing should depend on both predators and prey. And then we discussed the difference between linear versus nonlinear differential equations. And sneaking in here, we discussed the order of a differential equation. Anyone remind me what the order of a differential equation is?
It's the highest derivative that appears in the
Exactly. It's the highest derivative that you're taking when you're looking at the equation. And then we discussed linear versus nonlinear differential equations. So it turns out that and can anyone remind me what the general shape of a linear differential equation is? And yes, there are office hours after this class, so I'm happy to discuss any questions you have after class. So Let's say, once again, that our differential equation is going to be written as f of t, let's say u of t, u prime of t, u double prime of t, all the way up to u to the nth derivative of t. So this is going to be some equation, setting this equal to 0, is going to be an order m differential equation. What conditions should I ask for such that, or I could even write equal to g of t perhaps. Well, let me keep it at 0. What condition should I ask of this function f so that it's a linear differential equation?
So like you should be able to multiply like t and u of t and so on by like a singular constant and like be able to pull that out.
Exactly. So it's so there are two ways to think about it. I'll go back over this again. Two ways to think about linearity. In the variables u of t, u prime of t, all the way up to un of t. One of them is the more formal way, which says that f of t comma u1 of t plus u2 of t, u1 prime of t plus u2 prime of t. If u1 and u2 are two different functions of t, all the way up to un of t 1 plus, oh, I'm sorry, excuse me. Oh, I thought I was going to sneeze. Sorry. I hope I haven't just blown out all your eardrums. u2 of n of t. This whole function should be able to be written as a function f, the same function f of t, u1, u1 prime, all the way up to u nth derivative 1, plus f of t u2, u2 of u2 prime, all the way up to un of t. Or sorry, u2 nth derivative. And then we also have a condition on the constants, where if I multiply all of these variables by some constant c, I can kind of pull that constant out. So this, and then the f of t cu prime all the way up to cu n is equal to c times f of t u prime all the way up to un. So this is kind of the conceptual definition of a linear differential equation, but a more tractable way to think about these differential equations is that f of all these variables is going to be equal to some function only depending on t, a(n) of t times u to the nth derivative plus a(n minus 1) of t times u to the n minus first derivative, all the way down to plus a 1 of u first derivative plus a 0 of t times u plus some extra function f of t, all this being equal to 0. So the linear part is that all of the derivatives are on their own and they're only being multiplied by a function that depends on t. So this is our kind of other definition of linear, or way to think about linear. Okay, and we did some examples last time, yesterday, about some differential equations which are linear and some differential equations which aren't linear. Is there a question? So one thing that I want to mention before we move on is that an important technique is to try to model nonlinear differential equations with linear ones. And there's a very nice example that came up in my physics class, and it's also written down in the book. So it's a kind of a quick example to grab a hold of. And it comes from physics, like a lot of our examples will. So an example is the following. If you want to find the equation of motion of a pendulum, so motion of a pendulum, using Newton's second law and F equals ma, and writing down your kind of force diagram for the pendulum at a particular point, you'll find the following equation: d squared theta of t over dt squared. So it's a second order differential equation in the variable theta, where theta is telling you what the angle of your pendulum is at a particular point in time, plus g over L times sine of theta is equal to 0. So question, is this a linear or a nonlinear differential equation? Indeed, it's going to be a nonlinear differential equation, thank you, Madison, because I've got a sine of theta, and sine of theta doesn't fit my description of a linear differential equation, because all I want are the variables d squared of theta, d squared theta dt, d of theta dt, and theta, and then possibly a function of t. So the sine of theta makes things nonlinear immediately. However, there's something called the small angle approximation. Which says, essentially, that when theta is very small, theta is relatively close to sine of theta. Let me kind of draw a picture of this, perhaps. So, I mean, this is a kind of just an observation that if you look at the graph of sine of theta, oh wow, that's a bad sine of theta. And then you look at the graph of theta, so this is t, this is theta, this is sine of theta, and this line, which was supposed to be theta of t. Theta of t is equal to t. Sorry, this should be sine of t. Essentially what I'm saying is that for very small values of t, the line, the diagonal line, theta is equal to t, and the function sine of t are very close to each other. So for small angles, we can approximate sine of theta by theta. And so what often comes up in physics classes is that you write down the equation d squared of theta of t over d of t squared plus g over L sine of theta of t is equal to 0. And then you'll try to model this equation by d squared of theta of t over dt squared plus g over L, here's g is gravity, times theta of t being equal to 0. So this is the small angle approximation. And the idea is that as long as the maximum angle that your pendulum will experience is rather small, then these differential equations should be very close to each other. And so what physicists often do is they end up only solving this equation, and then they this is a linear differential equation, right? Because we've only got things involving the second derivative of theta, the first derivative of theta, and just theta. They solve this and they say this differential equation should be valid. It should describe the motion of the pendulum as long as the angle of the pendulum is small. So here we are essentially using this technique of approximating a nonlinear differential equation by a linear differential equation in some cases. Any questions about this? Okay. So essentially, we have now discussed a whole bunch of different types of differential equations. And the last thing that I want to do before we get into the next chapter, the next section, is to discuss our main questions. So the first question is, given an arbitrary ordinary differential equation, like f of t, u prime, all the way up to the nth derivative of u, where here u is a function of t, is equal to 0. Will this differential equation always have solutions? And the general answer is no. But with some very small or relatively small conditions, or relatively weak conditions, the answer will be yes. So the thing that you should think about here is, do all differential equations, if you just write down anything completely general, will this have solutions? That is, a function u such that it actually satisfies this differential equation? The answer is it does. It's not necessarily the case that all differential equations have solutions, but all of the ones that we are going to work with in this class will have solutions. And there's a relatively weak condition that we'll explore in chapter 2 about when differential equations have solutions. So first question is, when will it have solutions? The second question is, when will the solution be unique? And uniqueness already comes with some caveats, right? Because we've already seen that we've got no hope in general of actually having unique solutions, right? Why are solutions not in general unique?
Because they come in families.
Exactly. Well, first of all, diffie-qs, or solutions to diffie-qs, come in families. So if you just say, is a solution to a differential equation unique? The answer is almost always no. But what we did notice is that if you specify some initial data, some initial thing that you want your solution curve or your solution function to satisfy, but if we specify some initial data, or maybe I'll say some additional data, then it's possible. And what I mean by initial data is something like, I want u to satisfy f of, I don't know, t, u, u prime, u double prime, and I want u of 3 to be equal to 7 or something like that. This is like saying I want u to satisfy the system of equations, and when the time is equal to 3, I want this function to be 7. Maybe this refers to the height of a object or the population of something, right? But essentially, when you specify additional data, you can hope to have unique solutions. So essentially, the idea is often IVPs, or initial value problems, can have unique solutions. And then the last question or problem is to solve the Diffie Q. Can we find an explicit function which actually solves a given differential equation? And the answer is, on one hand, in the grand scheme of things, we can solve relatively few differential equations, but we can solve enough that it's worth at least this course and more courses. So even though it'll feel like we can solve a lot of differential equations at the end of this class, even though the grand scheme of things, one should say that we can't solve very many differential equations. It's kind of like integration in that sense. You go through Calc 2 finding a lot of functions that you can integrate, kind of tricky functions, but at the end of the day, they're really kind of just a drop in the sea compared to all of the possible functions that you might want to integrate. Okay, so this is our introduction. This is our chapter 1. Are there any questions about this material so far? All right, if there are no questions, then let's get started in earnest. Okay, so what we're going to be doing now is we're going to start examining first order ordinary differential equations. Linear. First order linear ODE. So can someone tell me what the most general first order linear ODE looks like?
dy dt plus p of t times y equals g of t?
Yes, more or less. I'll write it slightly differently. I'll write p of t dy dt plus q of t y of t is equal to g of t. And if you subtract over the g of t, then you can see that this is exactly something like f of t, y, and y prime being equal to 0, where all of the coefficients are functions that only depend on t. So this is the most general linear first order differential equation, ordinary differential equation. Now every time that I say something, I'm going to be throwing around these million words associated with the classification. Okay. So here is a first idea. First idea for how to tackle some of these. In some cases, in some extremely rare cases, the left-hand side above here might look like a product rule. Right? Just as written, it already kind of looks like a product rule. This would be a on-the-nose product rule if Q of t was the derivative of P of t. Because then we could write, take the derivative of the whole thing, and then here is where you apply the derivative to the function y, and here is where you apply the derivative to the function q. So let me do an example of this kind of extremely fortunate differential equation that might appear in nature. Let's take the example of t cubed plus e to the t, some function of t, times dy of t dt plus 3t squared plus e of t times y of t is equal to 4t. Right, so this is one of these extremely fortuitous cases where by some happenstance, this is exactly the outcome of applying a product rule to which function? How can I rewrite this left-hand side?
That'd be the derivative of y of t times t cubed plus e to the t.
Exactly. This is the derivative of e to the t plus t cubed times y of t. Right? And this is equal to 4t. So essentially, the trick is, or one idea is that one should hope that the left-hand side can be written as a product rule. And in this case, we were able to do it. Once we're here, all that remains is to take antiderivatives, because really what I want is y of t all by itself. If I've got a d of t in the way to undo that is to take antiderivatives. If I take antiderivatives here, I'll get e to the t plus t cubed times y of t. It's going to be equal to the antiderivative of 4t, which is 2t squared. And then I get y of t is just equal to 2t squared over e of t plus t cubed. Oh, I need to have a plus c. Of course, this is something that I need to be very careful not to forget. E of t plus t cubed. Right, so when I take the antiderivative of both sides, I'm gonna, essentially if I take the antiderivative of both sides, I should pick up a constant on this side and a constant on this side, but I'll just subtract the constant on this side from the constant on this side, so I only am dealing with one constant. And then I get a general family of solutions to this differential equation. First order linear ODE. Any questions about this? Now, the point is, this situation, this happy situation, is extremely rare. Right? Because for this nice happenstance to work out, you need q of t to be exactly the derivative of p of t. And if you change even one little thing about this function, then all of a sudden it won't be the derivative of p of t anymore. So the idea is as follows. We can often find some function mu of t, which gives us more freedom. This is called an integrating factor. Mu of t is called an integrating factor. And the idea is, if I look back up at this equation, it's quite possible that p of t dy of t over dt plus q of t y of t equals g of t. It's quite possible that q is not directly a derivative of p. But if we change this whole equation by multiplying by the integrating factor, then we'll get mu of t times p of t, dy of t over dt, plus mu of t, q of t, y of t, is equal to mu of t, g of t. And the thing is, we're letting mu vary more or less. We're trying to think of, is there a possible mu such that mu of t times q of t is the derivative of mu of t times p of t? And the answer is, this actually gives us a reasonable amount of leeway. So we can solve equations of this form where we didn't start off with q being a derivative of p. So let's do an example of this. Okay, so a first example. Let's work with the following differential equation. Let's do this one. Dy dt plus 1/2 y is equal to 1/2 e to the t over 3. So at the first glance, does this left-hand side look like a product rule? Well, not quite, because the function in front of the dy over dt is 1, and 1/2 is not the derivative of 1. So it actually looks quite different from a product rule, right?
Sorry, can you clarify what the exponent is on the e?
Oh yeah, t over 3.
Thank you.
Yeah, sure. So this is, so I'll just write over here, the left-hand side is certainly not a product rule. Or the image of a product rule, perhaps, is a better way to say it. But if we multiply by some unknown function, so essentially the idea is we're going to multiply by some possible function and check, is it possible to find a mu such that when I multiply, it does look like a product rule. So now let's change this differential equation to mu of t dy dt plus 1/2 mu of t y is equal to 1/2 mu of t e to the t divided by 3. Now the question is it ever possible to find a function mu of t such that the derivative of mu of t is equal to 1/2 times mu of t? Could this be a product rule? This left-hand side be a product rule? And the answer is yes. This left-hand side now can be a product rule. So what we're asking, can we find a function mu of t such that d over dt of mu of t is equal to 1/2 mu of t? Right? Because if this condition is satisfied, then this is indeed a product rule. And we can solve this quite literally. The technique for solving this is dividing both sides by mu of t. So we're looking for d over dt of mu over the function mu being equal to 1/2. What does the derivative of mu over mu look like? Exactly. This looks like the derivative of natural log. We can recognize this. A lot of differential equations comes from recognizing certain identities. this looks like the derivative d over dt of the natural log of absolute value of mu of t being equal to 1/2, right? Because if I take derivatives, then I'll recover exactly this, this left-hand side. And we know how to undo this process. If the derivative d over dt of natural log of mu of t, absolute value of mu of t is 1/2, then I can actually find mu of t on the nose. I first integrate both sides. So I get natural log of absolute value of mu of t is equal to 1/2 times t plus c. And then I raise both powers, or I raise both sides. I set both sides as the exponent of e, and I get absolute value of mu of t is equal to some 1/2, or e to the c times e to the 1/2 t. And then you remember the whole business about if I've got absolute values over here, then essentially a general solution will be mu of t is equal to some, I'll write it as b, some constant b, e to the 1/2 t, right? So any questions about what I have done in this collection of steps?
All right, can you explain where the b came from?
Yes. So e to the c is some number, some constant, right? Can e to the c ever be a negative number?
No.
No, it can never be a negative number. So the idea is that I take this equation, absolute value of mu of t is equal to this thing, and I break it into 3 cases. Either mu of t is positive for some t, it's negative for some t, or it's 0. If it's positive, then I just get mu of t is equal to e to the c times this thing. If mu of t is negative, then I get negative mu of t being equal to this thing, and then I just multiply by the negative on the other side. And then if it's 0, then that would be the same as asking for the constant in front of e to the 1/2 of t to be 0. So essentially, the 3 cases are mu of t is greater than 0, in which case my solution is e to the c, e to the 1/2 t. I get mu of t is less than 0, in which case I should look for the solution e to the negative, or negative e to the c, e to the 1/2 of t, or mu of t is equal to 0, in which case I really want 0 times e to the 1/2 of t. So the point is, all of these different ways that I can break up this side all lead to me just asking for some constant in front of e to the 1/2 t. So this is the general, this covers all of the possible cases.
Is
So,
it possible for, you can go ahead.
Sorry, are you saying that b equals either 0, -1, or 1?
No, I'm not. I'm saying for any constant number b, this will satisfy the required differential equation that when I take the derivative, I get back 1/2 times the original thing.
Oh, okay, thank you.
Yes.
Is it possible for the mu of t to equals to 0? Because I thought that e to the c is like approaches 0 but cannot reach 0.
The thing that I am trying to point out with this solution is that mu of t being 0 satisfies this differential equation.
Yeah.
Because the derivative of 0 is indeed 1/2 of 0. However, mu of t being equal to 0 is not a solution that we found. It's not of the form e to the c times e to the 1/2 t, right?
Yeah.
So in this step, all that I am saying is that given this equation, we can find all possible solutions to this differential equation by letting the constant in front of the exponent term vary and be anything. Whereas up here, we're only looking at when the constant is a positive number.
Okay.
So really all that I'm doing here is getting the most general solution. Now, of course, remember that I'm not just solving this differential equation for fun. I'm solving this differential equation because I want to use it to reinterpret this differential equation, right? If mu of t is 0, then I'm getting a very silly differential equation indeed, which is just saying 0 plus 0 is equal to 0. So even though this is the most general form, I don't really want to think about this. Like all that I need is one solution to this differential equation, one non-trivial solution that I can plug in back here. So even though I went through this work to find the most general solution, all that I need for my integrating factor is I need to pick a nice solution. So let's let mu of t be equal to e to the 1/2 of t. This is one solution in this family, and any solution in this family will do the trick of making this equation look like a product rule. So let me do it explicitly, and you'll see what I mean. Let mu of t equal to e to the 1/2. Then my equation above becomes e to the 1/2 of t times dy over dt plus 1/2 e to the 1/2 of t y is equal to 1/2 e to the 1/2 of t e to the t over 3. This is just what happens when I plug in some given solution to this differential equation, this kind of auxiliary differential equation, back in for my mu. I get this. Now, does the left-hand side look like a product rule?
Yes.
Yes. I can now rewrite the left-hand side as d over dt of e to the 1/2 t times y is equal to, if I simplify over here, 1/3 plus 1/2 is going to be 4/6.
Would the right hand side be multiplied by 1/4, not 1/2?
No, I don't think so. Why do you say it should be 1/4? Up here my equation was 1/2 mu of t times e t over 3. Right?
Oh, okay, yeah.
Right, and if I pick that one, then I should just have this thing right here.
So in this situation, the right-hand side doesn't really matter. It's just
It doesn't
making the-
matter yet. It will matter at the end of the day, but it just doesn't matter very much at the current moment.
okay.
Since we just chose B to be 1, is there ever like a time when we can't do that?
So one point that I should make right now is that actually every b that's not equal to 1 would give me something helpful except for the 0 solution. So let me just write as a kind of like, what if we took like negative pi times e to the 1/2 t, right? This is this is another one of the solutions to the kind of auxiliary differential equation. And then our function would look like this. It would look like negative pi e to the 1/2 t dy over dt plus 1/2 times negative pi e to the 1/2 of t y is equal to 1/2 times negative pi e to the 1/2 of t times e to the t over 3. And I just want to point out that this also is a product rule, because it doesn't matter which constant you take here. I can still write this thing as d over dt of negative pi e to the 1/2 of t times y. So me picking b to be 1 was just a matter of convenience. All I need is one integrating factor which satisfies the correct differential equation. So why not pick the nicest one when I'm thinking about this? Any b except 0 would give me nice answers. I just picked the nicest one and saw what I got. Okay, so getting back to the differential equation that I've now produced, I have now gotten the following differential equation. D over dt of e to the 1/2 of t times y is equal to 1/2 times e to the 5/6 of t, right? 1/2 gives me 3/6, and 1/3 gives me 2/6, so I get 5/6. Are we okay with how I have gotten this differential equation? I should remind you that it comes from this differential equation where I plugged in mu of t is equal to e to the 1/2 t. Any questions? Okay, so now, of course, I'm in a position where I can actually solve this differential equation. And now is where the right-hand side is going to be important again, because I need to take antiderivatives of both sides. If I take the antiderivative of the left-hand side, then that's easy. It's just going to be e to the 1/2 of t times y of t. Oh no, I hope my pen doesn't run out. And then if I take the antiderivative of this side, it's going to be what? 6/5, right? 6/5 e to the 5/6t plus c. If I take the derivative of this, I recover this. Yeah. And now I can finally solve out for y of t. Y of t is now equal to, I just divide everything by e to the 1/2 t, so I'm going to get 3/5 e to the 5/6 minus 1/2 is 2/6, 1/3, plus c over e to the 1/2 t. Any questions? Something that you can always do to check your work is remember that a putative solution, I'm going to switch pens. A putative solution you should always be able to check by just plugging back in. So what I definitely encourage you to do is check. Well, let's do it. There's no reason not to. Check. This is a solution to the original differential equation, dy dt plus 1/2 y is equal to 1/2 e to the t over 3. On the left-hand side, it's asking me to take the derivative of y of t. The derivative is going to be 1/5 e to the 1/3 t plus 1/2 times this whole thing times 3/5 e to the 1/3 t plus c times e to the negative 1/2 t. This should be equal to 1/2 e to the t over 3. Did I do this right? Does this work out?
For the dy dt, shouldn't you include the c over e?
Oh, I forgot to take that derivative, yes. So dy over dt is going to also be plus, now here I'm going to get a negative 1/2 c e to the negative 1/2 t. And that's going to be very good because then I'm going to get a cancellation, right? This 1/2 c e to the negative 1/2 t will cancel with the negative 1/2 c e to the 1/2 t, and I'll be left with 1/5 e to the 1/3 t plus whatever this coefficient is of e to the 1/3 t, and that'll end up being 1/2. So indeed, this works. Thank you for reminding me that I forgot to take the derivative of this chunk. So indeed, I have found a solution to this differential equation, the original one that I started with. But what I had to do is I had to find the correct integrating factor. I had to multiply everything by a mu of t and then figure out what mu of t had to be so that the left-hand side looked like a product rule. Any questions here? And once again, notice that this is actually a family of solutions to the differential equation. And if you wanted to find a particular solution, say at y of 0, if I wanted y of 0 to be 1, then I would set all the t's equal to 0. I'd set this side to 1, and then I would solve for t and find a particular solution. So once again, we see you have no hope of the solutions to a differential equation being unique, but if you specify some initial data, like y of 0 or y of 5 or whatever, then you have the hope of having a unique function which solves your differential equation and passes through a given point. Any more questions? No? You're all very quiet. Okay, well, I guess there's nothing I can do about that. Let's work in slightly more generality. So, slightly more general. Let's consider dy over dt plus ay equals to g of t. There are a couple things that I want to kind of express here. We're in the same, here a is a constant. A is a constant. A is in, I don't know, R, not 0. So this is going to be almost identical to the previous problem. A is not the left-hand side is not immediately a product rule, but once I multiply by the correct integrating factor, it will be a product rule. So to solve this, I'm going to write mu of t is equal, or sorry, mu of t times dy dt plus a mu of t y is equal to mu of t g of t. And we're going to see pretty quickly that a successful integrating factor, mu of t being equal to e to the at, will work. And by that I mean it solves the differential equation, the derivative, d over dt, of mu of t is equal to a times mu of t. Many other things would work, namely, all that I need to do is multiply this by a non-zero constant, and that would also satisfy this differential equation. But when I'm looking for an integrating factor, I just need one function that does the trick. So I'll pick the nicest one, where the constant is just 1. And so then the solution, sorry, so the general solution, now we can rewrite, and we get d over dt of e to the at times y is going to be equal to the left-hand side. This will be equal to g of t times mu of t. Right? Am I going too fast here, or is this comprehensible? The one bad thing is that I don't have a lot of metaphorical board space, so you can't see the original differential equation. But I started out.
Could you?
Yes?
Yeah. Could you go back and show that last part real quick at the end of the bottom of the page?
Yeah.
Cool. Thank you.
Exactly. So I go from here I need to find a mu of t that satisfies this differential equation. Mu of t equals e to the at will work, so I just plug in e to the at for all of the mu of t's. So maybe I'll write this here. This
So
will
you-
give me, oh, yeah.
Sorry, so I just want to make sure you got that in the same way that we solved the other one. You just skipped all of the.
I just skipped all of the steps because they are the same. I
Okay,
just
I just wanna
divide
make sure.
both sides by mu of t. I recognize that d over dt of mu over mu is the derivative of the log of the absolute value of mu being equal to a.
Got
And
it.
I raise both sides by e. Yes, so it's the
Perfect.
exact same step.
Thank you.
So here, this is going to be e to the at dy over dt plus a e to the at y being equal to e to the at g of t. And this left-hand side, I can recognize exactly as a product rule. This is exactly, let me rewrite this as g of t times e to the at, right? We happy with this, this step? And once we're here, we can immediately take antiderivatives. So the antiderivative of the left-hand side is easy. I just get e to the at times y. And now this is going to be equal to, I need to take the antiderivative of g of t e to the at. Now, thus far, I mean, sometimes it's quite possible that g of t times e to the at might not have any elementary antiderivative. There's no guarantee that I can express this as the derivative of elementary functions. But I can always use the fundamental theorem of calculus. So I can always rewrite this side as the definite, or the, sorry, not the definite integral, the indefinite integral from t0 all the way up to t. I have to replace variables, g of x e to the ax dx plus some constant c. Right? This is the fundamental theorem of calculus. Tells me that if I ever take the derivative with respect to t of this function, I get exactly this, right? So this is the general form of the antiderivative here. It's possible that sometimes I could express this in terms of nice functions, but this is a general expression that will always work. And then I get y of t is equal to 1 over, or e to the negative at times t naught up to t, g of x, e to the ax dx plus c. This is a general solution to
Sorry.
differential equations of the form above. Yes?
What does it say after the y of t equals?
This is e to the negative at.
Okay.
I just divided both sides by e to the at, or multiplied both sides by e to the negative at.
Okay, thank you.
Yep.
Sorry, I don't fully understand the purpose of, like, I'm a bit lost from the first line to the second line.
First line to the second line. Right. Let me think if I can come up with a good example. Essentially, what I'm just trying to get here is there are some functions, g of t, such that that function times e of at doesn't have a nice antiderivative in terms of elementary functions. Like, not every function has an elementary antiderivative. Are you okay with that?
Yeah.
So even if you can't write the antiderivative of this function in terms of nice functions, I can always write this function as an antiderivative. So by the fundamental theorem of calculus, by the FTC part 2 usually, d over dt of t0 up to t of g of x e to the ax. I mean, let me just do it generally. The derivative of a function written g of x dx, what is this equal to?
GT.
GT, exactly. So all that I'm saying is, if this function doesn't have an antiderivative in terms of nice functions, I can still always write this for its antiderivative, because the derivative of this with respect to t will get me this back.
Okay, and so the EAX is just like
I just have to change
general-
variables. Yeah.
Okay.
Yeah, the x is a dummy variable, as it's called. So remember that this thing is a function of t, and t0 is some arbitrary base point. It doesn't
Right.
matter for the computation of the derivative of this function.
I see. Okay.
Why do you need the plus c? Shouldn't that just like cancel out?
What should it cancel out with?
Like when you do the fundamental theorem of calculus, like the plus c cancels out.
No, I don't think so. And one important thing to remember is that if I didn't have a plus c, then this function right here is just determined, I believe. This is just some function that I evaluate. Of course, it depends on which t0 you fix as a base point, but you have to fix some t0, and then the c is allowing me the wiggle room so that if I prescribe like y of 0 is equal to 100, if I need to solve an initial value problem, then I need to be able to mess around with the c. Anyways, the point is the derivative of this function equals this. And I shouldn't remember that when I take antiderivatives, I always need to add on a constant. Right? This is the most general way of writing all possible antiderivatives of this function.
Okay.
And the point is, you shouldn't neglect that. You shouldn't forget to get the most general possible family of antiderivatives.
Is that common, like in the course, that we'll just use a general form like that instead of evaluating an actual expression?
Yeah, I'll definitely, now that I've told you about it, I have to put a problem on one of your exams where you can't actually take the antiderivative and you just have to leave it in this form.
So I'm a little confused about what like the reason is for using like the fundamental theorem of calculus at the end, because I would think that like once you have y of t, like I would just stop there. So what's the point of using that last step?
This is like a remark. This is the answer.
Okay.
And the explanation is, why am I writing this as the antiderivative of this? And the answer for why this is the antiderivative of this is fundamental theorem of calculus.
Okay, I got you. Thank you.
Yeah. So this is the general form of this equation, of solutions. So now I would like for you to do an example. So, oh wait, can I do? Yes, this is a fine one. So why don't you work out the following example? So find a family of solutions to the differential equation given by y prime plus y is equal to t e to the negative t plus 1. And I'll give you, 5 minutes, say. How are people doing on this problem?
I still need a bit more time.
Sure. Perhaps one thing I can ask is, have most people found the correct integrating factor to use?
I think so.
I'll give a minute or two and then at least write down the integrating factor. Actually, I'll just write down the integrating factor that works right now. Mu of t equals e to the t works. And actually, so does any c e to the t, but here is an integrating factor that does the trick. All right, I'll say just a little bit. The first thing is that if I rewrite this into dy over dt plus y is equal to t e to the negative t plus 1, then this is exactly of the form that I was discussing above, where a is equal to 1. So that's kind of a quick way to see that the integrating factor ought to be e to the t. So if we change this whole differential equation by multiplying everything by e to the t, we get dy over dt e to the t plus e to the t y is equal to t plus e to the t. Did most people get here?
Yeah, I did.
Yeah.
Yeah.
Great, great. So the next step is to recognize that after we've made this change, after we've multiplied both sides by the nice integrating factor, then the left-hand side can indeed be written as the image of a product rule. So I can rewrite as d over dt of e to the t times y is equal to e to the t plus t, right? And now what's the next step?
Integrate.
Yeah, take antiderivatives of both sides. I get e to the t times y is equal to e to the t plus t squared over 2 plus c. Can't forget that when I take antiderivatives, I need to pick up a constant. And then I just divide, so I get y of t is equal to 1 plus t squared e to the negative t over 2 plus c e to the negative t. This is the general form of the solution for this differential equation. And if I wanted, I could ask for some initial value. For instance, to get a unique solution, an IVP would be, or initial value problem would be, find a function satisfying this differential equation such that, I don't know, y of 5 is equal to 18 or whatever. This will be messy. You'd need a calculator or something to solve it because you have to, it's going to be messy, but once we do this, we'll be able to uniquely solve for c and have a unique solution to this differential equation such that y of 5 is equal to 18. Any questions here?
For this type of problem, would you have expected us to like do the ln part, or do we just like use the e to the at like notation?
So the ln stuff was work that we did to show that this sort of integrating factor works. I would say that you're going to do kind of a lot of these sorts of problems, so it'll become kind of consistent where you'll be able to pick out the right integrating factor, and you can maybe skip over the natural log part where you're actually solving that kind of secondary differential equation. In general, if you find the right factor of integration, then you're doing it correctly, you know. But don't forget that we actually had to solve a secondary differential equation originally to get the function mu of t that works.
Okay.
And as my last thing, I'm going to do something even more general, which will kind of bring that sort of idea back in play. So we're kind of moving up through the hierarchy of how challenging of first order linear differential equations we can solve. Now, let's find a general solution to this. So maybe most generally for linear first order differential equations, we're going to have something like dy dt plus p of t y is equal to g of t, right? Earlier, we were just saying, what if p of t is equal to a? Then we know how to solve it. But if p of t is an actual function of t, then things might be a little more challenging. But it turns out they're not that much more challenging. We can still use the technique of integrating factors to make this work. So is this left-hand side a product rule? No, but after multiplying everywhere by an integrating factor, we'll be able to make it look like a product rule. So we multiply everywhere by mu of t, dy over dt plus mu of t, p of t, y is equal to mu of t, g of t. So now what is the condition that I need to ask of mu such that the left-hand side is a product rule, or is the image of a product rule? Okay.
The derivative of mu of t has to equal mu of t times p of t.
Exactly. d over dt of mu of t is equal to mu of t, p of t. And now we're back in the exact same situation. We know how to solve, if not explicitly, we know how to solve generally this kind of differential equation, once again by passing to natural logs. So I'll kind of go through that process again here, but just remember that p of t might be some sort of tricky function. So we're going to solve this auxiliary diffeq to find the correct mu of t. And we do the same thing that we've been doing this whole time. d mu over dt over mu is now equal to p of t. All these things are in terms of mu. So we can rewrite this as d over dt of natural log of mu of t is equal to p of t. And now if we want to solve, we have to take antiderivatives of both sides. If I take antiderivatives of both sides, I'm left with natural log of absolute value of mu of t is equal to, once again, p of t might not have an integral or an antiderivative in terms of elementary functions. So if I want a fully general answer, the best thing that I should write here is that this is the antiderivative from t0 up to t of p of x dx plus c. So this is exactly the same as I was doing before. I'm just saying you can't always necessarily write down nice elementary antiderivatives of functions. And when you can't do that, you can still always write this expression and it'll still be correct by the fundamental theorem of calculus. So what we get down to at the end of the day is that mu of t being equal to e raised to the power of this function, t0 up to t, p of x dx, will work. There exists some function such that this differential equation is satisfied. And if you actually write out mu of t is equal to e to the antiderivative t0 up to t px dx and plug it in here, you'll see that this left-hand side is a product rule. Okay.
Are we technically missing like the some random constant out the front that we're just assuming to be 1 here?
So yeah, essentially we're doing the same thing where we're solving an auxiliary differential equation. We're going to get a family of solutions. But what did we want up here? We just wanted one function which satisfied the differential equation. Any function that satisfies the differential equation will allow me to rewrite this original differential equation in a better format. So here I can just pick the nicest function that satisfies the differential equation. And for me, the nicest one is going to be when c is equal to 0. And so we'll just end up with exactly this. Does that make sense?
Yeah.
Not really?
Oh, no, I said thank you.
Oh, thank you. Okay. So yeah, there are a lot of mu's that could make this left-hand side a product rule. Pick one. And I picked the nicest one. So once we have this, then we can write the left-hand side as, so once we find the right mu, and this is some expression for the right mu, this left-hand side becomes d over dt of, what do I want to write? Mu of t times y, being equal to mu of t, g of t. And this is the correct form of mu of t that'll do this. And then once you're here, we can just kind of proceed formally, right? I know how to solve this again. So once again, I have to take antiderivatives of both sides. And once again, I'm going to run into the issue that it might not be possible for me to write the antiderivative of this function in terms of nice elementary functions. So the next step would be mu of t times y is equal to this function of t, t0 up to t of mu of, I'll use a different dummy variable now, mu of z, g of z, dz, plus some constant. And then my final answer will be y of t is equal to 1 over mu of t times this thing, 0 up to t, mu of z, g of z, z plus c. And if I were to be even more explicit, I could write out these mu's in terms of this integral. So you'd actually have two different functions where the functions are defined via integration floating around for the general form of this solution. So it could look very messy, is the point that I'm making here. But nonetheless, we can find solutions to differential equations of this form. And we can write down something explicit like this that will solve the differential equation.
I have a question.
Yeah, sure.
In the equation for mu of t, did you leave out the constant on purpose in the exponent of e?
Yes, I did. So remember that what I'm doing is I'm trying to find a mu such that the left-hand side looks like a product rule, right?
Mm-hmm.
The condition for the left-hand side to look like a product rule is that the derivative of mu has to be equal to mu of t, p of t. So in trying to solve this original differential equation, or this original differential equation, I've produced a second differential equation that I need to solve for mu. But any solution will do. What I've written here is a possible family of solutions, where as you vary C, you vary the family mu of t that solves this differential equation. But since any single member of this family will do, I picked just a very nice one and basically forgot about the constant. Forgetting about the constant corresponds to picking a nicer looking solution, right? And then this solution will work. It's one of many that will work. And then I just plug this into my equation up here. Is that satisfactory?
That makes sense.
But once again, if you wanted to write down very miserable equations so that you can show it to your friends and tell them that you're doing crazy math, of course, I can rewrite this as times some constant b, and then everywhere I'm going to replace these mu's by b e to the nasty integral times dy plus b nasty integral p of t y, right? I mean, that's fine. You can do that as well. Just makes your formulas look messier. Which I actually hate. Don't do that.
I have a question.
Yeah.
I don't really get why in like the beginning of it, like why that makes it a product rule, like why that specific equation.
So let's actually work out this derivative. So I need to hold on to this mu of t is equal to e to the antiderivative t0 to t p of x dx. Please remember this formula so that when I write things on the other side of the paper, I write it correctly. So let's actually concretely check. What is the derivative d over dt of e to the integral from t0 up to t of p of x dx times y of t, right? This is explicitly what I wrote over here. And what we want to check is that the derivative of this thing actually recovers this expression up here. So we're going to actually take this derivative. It's going to be a product rule. So first I'm going to take the derivative of the second, just so that things look nice. It's going to be equal to e to this function, t0 up to t, p of x dx, times dy over dt. That's one part of the product rule. The other part of the product rule is I need to take the derivative of this function. What's the derivative of this whole thing? Well, by the chain rule, the derivative of e to the anything is just e to that something. So I'm going to get e to the to t0 up to t p of x dx. Now, by the chain rule, I need to multiply by the derivative of the inside function, right? If I'm doing a chain rule. What's the derivative of this top piece with respect to t?
It's p of t.
This will be p of t by the fundamental theorem of calculus part 2. So the derivative of this chunk is p of t. And then, to finish off the chain rule, times y. This whole thing is the same thing as mu of t dy over dt plus mu of t times p of t times y. So I can go back and forth. This thing, which is what after I multiply by the integrating factor, I get something that looks like this. And the point is, we did work to find the correct integrating factor so that this whole thing is equal to this, which is equal to d over dt of mu of t times y. Does that help?
Yes, thank you.
Yeah, of course. It's good to remember these facts about the fundamental theorem of calculus so that you're kind of comfortable again when I write down these expressions. They look ugly if you haven't looked at them in a while, but they have this very nice property that makes them very easy to work with. Okay, so we have done integrating factors. Starting next, so I'll give you homework on it, and then we'll also work out some more examples in class, and then next time we'll get started on section 2.2. All right, have a nice afternoon, have a nice Friday.
I have a random question.
Yeah, sure.
It was just like in the homework, it says find the equilibrium solution of like y and then a subscript e. That e just stands for equilibrium, right? Not some like not like for the actual natural exponent. So. Okay. And also, I just wanted to ask if, I guess more like reiterate because somebody else brought it up, that the like show work function, like typing it is like very slow. Like it takes like probably twice as long to type it in as it does to like type it out on paper. And I was just gonna, see if there's any way we could like submit like scanned like paperwork to like the Dropbox and Sakai or something like that.
So it turns out that there is a way that I can turn off the show work boxes, and I'll probably just do that.
Oh, okay.
So for future homework, I'm just gonna turn that off.
Okay, so for this homework that's due, do you still want us to put something in the show work, or because I think it lets us submit it without it, to be honest.
It does let you submit without it?
Well, I mean, I guess we could type in
I think that it says
our
it's
name or
incorrect. You
something.
can do it without it.
Okay,
well,
so I don't want to, I probably should, I can't change the assignment while it's assigned. So I won't change anything for the first 2 assignments that are in, but for future assignments, I will try to turn off all of the show your work boxes, so this shouldn't be an issue going forward.
I've been submitting without showing my work, and it's been fine, so.
Okay.
Okay, thank you. That makes it a lot easier.
Yeah, sure.
Thank you.
All right, have a nice Friday.
Thank you. Thank you.
Thank you.
Thank you.
Professor.
Yep.
I'm gonna step away for like